Okay, so let's just recap what we have done so far. Okay, we have covered what I consider to be, your three basic gas laws. Okay, pressure, volume, temperature, right? But guys, be aware, nowhere in the introductory section of this chapter, nowhere did I talk about an amount of gas, like a mass or a number of moles. Nowhere did I talk about that. We just dealt with pressure, volume, temperature. When you start talking about the amount of a gas, or you need to solve for the amount, you're using this guy, your ideal gas law, which absolutely should look familiar because you definitely used it in Chem 1. Okay? It is on your equation sheet. If you would look, guys, on the back side of your equation sheet, there is a section that says gases, liquids, and solutions. And it's right there at the top. All right, so let's just refresh our memory here. Okay, P obviously stands for pressure. You're going to see one of three units. Okay, atmospheres and torr are probably the most common. And remember, sometimes you'll see millimeters of mercury as a unit. That's the same thing as torr. On a very rare occasion, you may see the unit of kilopascals. Okay, but that's not very common. Okay, V is volume. Make a note to yourself, ladies and gentlemen. The units matter. Okay, if you're using a volume with the ideal gas law, it must be in liters. If you plug in milliliters, you're going to get a wrong answer. Okay, little n, that's moles of your gas. I'll come back to R in a minute. T is temperature, must be in Kelvin. Don't leave it in Celsius. And guys, R is called the ideal gas constant. And there's three possible values you could be using. All right? Do you have to memorize these? No, you don't. Okay? If you look on the right-hand side here, those values are given to you. Right? So there's no need to memorize them. Now see if you remember this from Chem 1. How do you know which one to use? Do you remember? Yeah. What are your units of pressure? Okay. If your units of pressure are atmospheres, you're using this guy. Torr, or millimeters of mercury, you're using this guy. And if you'll notice, on your equation sheet, the units written next to this number, on your equation sheet, you will not see kilopascals. I assure you it is there, okay? It's sort of hidden in these units, but it is there. It is the number you would use if you're in kilopascals. But again, kilopascals doesn't come up very often. Okay, now, if you think about it, guys, the word ideal, if you think about how you use that word in your everyday speech, you say things like, well, ideally, ... Okay? It means like in a perfect world, if everything was right and good. Okay? An ideal gas is a hypothetical substance. Okay? And this is a very kind of calculus way to think of it. A limit, okay, is something that you approach but never actually reach. Okay, so we can approach ideal behavior but never actually quite reach it. Okay, the best we can get for a gas to be, quote, ideal is in a situation where you have low pressure and high temperature. That's the best you can get to make a gas behave in an ideal fashion. Now, we're going to use the ideal gas law anyway, because it's a pretty good approximation. Okay, real gases do not behave in an ideal way. Okay, just like anytime you do an experiment, there will always be some kind of error. Okay, but we're going to use the ideal gas law because it's a good enough approximation. Okay, now we are going to combine the concept of gas laws and stoichiometry, and we're going to put them together. Some of you will have done this, some of you will not. Okay, here's the situation. Well, there's two situations actually. If you come across a gas laws stoichiometry problem, and the question says something about being at conditions of STP, standard temperature and pressure. Okay, which, just to refresh your memory, these are the conditions, and again, you don't have to memorize that. It's given to you. Okay, there's good stuff on here. What is this in Kelvin? 273. Okay, what is this pressure in torr, for example? 760? Thank you. Yeah, 760 torr or 760 millimeters of mercury. Okay, if the problem says that you are at STP, you are permitted to use that conversion factor. And let me be clear about this. That is the only time that you are permitted to use that number. Okay, so for example, let's say you are given a mass of reactant and you are supposed to calculate volume of a product. Okay, well, that's a stoichiometry problem. That would, to be more specific, would be a 3-step stoichiometry problem. If you're at STP, you are permitted to use that number. Okay, so what if you're not at STP? If you're not, then you will for sure be using the ideal gas law at some point in the problem. It could be at the beginning, it could be at the end. It depends on the problem. Okay, so let's look at some examples here. And guys, I apologize, I should have written the state of matter after HCl there, so just add this in. That's aqueous. Okay? It says use the following reaction. Anytime you're given a reaction, what should you immediately do before you read any further? Okay. Is it balanced? Yeah, it's balanced. It doesn't look balanced at first glance, but it is balanced. Okay. So number 1 says, and you're going to do these problems, I'm just going to sort of set it up for you. Calculate the mass of sodium bicarbonate. Where is sodium bicarbonate in this reaction? The first reactant. Okay, so I'm just going to put a little question mark grams, because that's what I'm supposed to find. Calculate the mass of sodium bicarbonate necessary to produce 2.87 liters of carbon dioxide. And it says we're at STP. Now, anytime you see that, you should be doing a little mental dance of joy, because that means the problem is relatively short, pretty quick, because you can use what number, ladies and gentlemen? Very good, 22.4 liters. Okay, so number 1 is pretty simple. Let's look at number 2. Let me just put that back. Okay, don't start doing number 1 yet, just listen. Okay, number 2 is a little bit more complex. Let's look at it. If 27 liters of gas are produced, stop right there. What gas am I talking about? CO2. Yeah, it's the only gas in the reaction. You need to pay attention to those states of matter. Okay, so let's make this more specific. 27 liters of CO2 are produced at 26 degrees, 745 torr. Stop there. Are we at STP? No. If you're not at STP, what must you use at some point? Ideal gas law. So I'm just going to write that down because I know I'm going to need it at some point. Okay, when 2.6 liters of HCl are added, what is the concentration? Okay, so let me write that down. What's a word I could sub in for the word concentration? Molarity, absolutely. Okay, so I'm going to write that in. And can you remind me, what's the formula for molarity? Moles over liters. Okay, great. Sorry, that's kind of hard to see. Moles over liters. Okay. The way that I typically will approach a word problem is somewhat working backwards. Okay. We are supposed to find the molarity of HCl. Do I know the moles of HCl? Yes or no? Is that given to me in the problem? No. Okay. I always circle my unknowns. Are we given a volume of HCl? Yes or no? Yes. Okay. So I have that. I can solve this problem if I can find moles of HCl. Right, so I'm going to come back to this equation, and I'm going to just focus here. If I can find that, I can solve this problem. Is HCl a gas? Yes or no? It's not a trick question. It is not. It has AQ written next to it. So, can I plug something relating to HCl into the ideal gas law? Absolutely not. Okay? That is a really common mistake. People want to use this equation with all kinds of states of matter. Remind yourself, it's the ideal gas law. So let's look at this and see, what do I have and what am I still missing? Right? This is always how I do gas law stoichiometry problems. Do I have a pressure to work with? Yes or no? Yes. I'm going to put a check mark over it because I've got it. Do I have a volume of gas? Okay, which gas are we talking about, by the way? CO2. And yes, I have a volume. Do I have a number of moles of CO2? Nope. I'm going to circle it. Do I have a value for R? Yes, I do. Okay. Was I given a temperature? Yes. So, this is what I want you to get started with. When you solve for N here, what units will your answer be in? Moles of what? CO2. That's not my final answer. If I have moles of CO2, remember what our ultimate goal is? Can I get to moles of HCl? Okay. Go. Do numbers 1 and 2, please. Check it. But guys, if you look at number 1, that's what I mean by if you are at STP, the problem is pretty simple. It's just a conversion. That's it. Number 2, a little bit more complex because it's not at STP. Now let me say something about number 2, okay? When you're in a situation that is not at STP, again, what I did immediately is I wrote this down because I know I'll need to use it at some point. In this particular problem, I used it first, and then I did some stoichiometry. It won't always be in that order, okay? And how would you know if it's not? This is how you would know, right? If you follow what I said, you see it's not at STP, you write down the ideal gas law. I like to go through and put check marks over my variables. What do I have? What do I don't? If at the beginning of the problem, you see that you don't have just one unknown, you have 2 unknowns, that means you can't use this yet, right? Which means you'll have to do some kind of conversion within the equation, some sort of stoichiometry first, and then you'll be able to use this. The stoichiometry will help you solve for one of those unknowns, and it's going to be moles of something. Okay? So it is not always in this order. So just be careful. Okay. So what else could we use the ideal gas law for? We could use it to find density. We could use it to find the molar mass of a gas. And ladies and gentlemen, if you're solving for a molar mass, you know, maybe I don't tell you what gas it is. It's some unknown gas. If you find the molar mass, then you could go to the periodic table and figure out which gas it is. Okay? But these are all things that come from the ideal gas law. Now, let me say something before I put anything else up. If you are more of a mathematically minded person and you are good at substituting one equation into another and isolating variables, you're going to love this. If you're not, I have something for you too. Okay? Tell me, please. Let's just make sure we're starting on the right foot here. If you have a mass, a number of grams, and you divide by the molar mass, grams divided by molar mass, what units do you end up with? Moles. Okay, fine. And let me call your attention to something, and this is honestly really annoying. Look on your equation sheet. Okay, the variables are defined on the right-hand side here. This capital M does not mean molarity. It means molar mass. Do you notice over here on the right-hand side, this capital M is in bold? Okay, it's in bold. Can you immediately see that? Probably not. Okay, I think this is a little, like, couldn't we have come up with a better variable to make it not so confusing? But they didn't ask me. Mass divided by molar mass is moles. And I'm going to plug that in. I'm going to substitute that in to the ideal gas law. Tell me, please, what is the equation for density? What divided by what? Mass over volume. You got it. Okay. What I'm going to ask you to do, mathematically minded people, please isolate, rearrange this equation so that M divided by V, M and V. M divided by V is on one side of the equation and everything else is on the other side. That's right, yeah. M, molar mass, times pressure, so big M times P over RT. Okay? The point is, you can use the ideal gas law to solve for density. You can also use it to solve for molar mass. Okay? Now, if that's super confusing to you, don't worry, I have something for you too. You can use this. Right? All I've done is rearranged it a little bit. D stands for density. Okay? Molar mass equals density times R times temperature divided by pressure. And are you ready for the way to remember it? It's kind of gross. Molar mass equals dirty P. Ew, gross. Okay, dirty P. Ew. Okay, this is another way to remember it. That is not on your equation sheet. Okay, so you will have to memorize it, but you really shouldn't have to, because you can, if you can substitute things in, you can always rearrange for whatever you need. So, here's what I want you to do, okay? I want you to do these two problems. Let me just give you a quick little heads up here. Just take a glance at number 2 before you start writing anything down. You are given an empirical formula, and ultimately you're supposed to find a molecular. Ladies and gentlemen, think back to chapter 3. What is the one piece of information you need to go from an empirical formula to a molecular? Molar mass. Okay? Well, do we have a way to find that? Yeah, look on the previous slide. We do. Okay? Go to it. Okay, so you can't do this problem unless you know the formula for ammonia, which you should all know. Then you can solve the problem. Okay, I'm just going to pull up number 1. And guys, I have left the units off on purpose because I want you to help me figure out what they are. Okay? Guys, whenever you have a density, the units are always unit of mass per unit of volume. Okay? And they can be all kinds of things, but what do you think, what do you think the unit of mass is in here? Go with your gut instinct. Grams. Okay. Mass per unit of volume. What unit of volume? Liters. How'd you know that? How did you know it wasn't like milliliters? Okay. The ideal gas constant here has units of liters. Also, remember, this came from the ideal gas law, and your volumes are always in liters for the ideal gas law. Okay, so there's number 2. And let me just say again, did I have to use this equation? No. I could have used any equation that involves molar mass, because that's what I needed to find. And remember, an empirical molecular situation, you were given the empirical, which I just looked to my periodic table to get this number. I could see that the molar mass that I solved for is just about double of this one. So that's why I did this. That's a really common situation in AP Chem where you'll be given the empirical, you're supposed to find the molecular, and there's a whole variety of ways to find something's molar mass. Okay, but that's a very common situation. So our last topic of the day is the concept of partial pressures. Okay, and all that means is, if you have some sort of container, maybe a balloon, and you know how much I love balloons. Okay, what if our balloon does not contain just helium? what if that balloon contains helium and carbon dioxide and some oxygen? Okay, well, each of those gases has its own what we call partial pressure, right? And that's what these are representing. This equation is on your equation sheet. And what I mean by dot, dot, dot is it doesn't have to be a mixture of 3. Maybe it's only 2, maybe it's 4, maybe it's 8, maybe it's 20 different gases. It doesn't matter. The point is the partial pressures of each one added together will be the total pressure in that balloon or that container. Okay? What else could you be dealing with? Well, maybe you're just focused on not all of the gases, but just one of the mix. This equation is also given to you. You don't have to memorize it. This is representing the partial pressure of that one gas that you're focused on. Okay, this is the total pressure of the whole system. And this is something called the mole fraction. And again, if you look at your equation sheet, it is defined for you right there. Okay? And if you think about it, guys, the word fraction, any kind of fraction, is always the same thing. Part divided by whole. And that's exactly what this is. It's moles of the gas that I care about, gas number 1, divided by the total gaseous moles. Let me call your attention to this word fraction, okay? This word is a little bit of a misnomer, okay? Let's say you are asked to solve for x. Please don't leave your answer as a fraction, okay? We don't do fractions in chemistry. That's for math. If you're asked to solve for this, please divide it out. Give me a decimal. Okay? And let's talk about what are the units for this. I mean, think about it for a second. Moles divided by moles. What happens when you have the same unit in numerator and denominator? They cancel out. So, what? It has no units. It's a unitless entity. All right? So, you're going to do these. Let me just say something that 1 and 2 are connected. So, information that you find in number 1 may be used down in number 2. Okay? Look at the 2 equations on the previous slide. Figure these out. Yeah, guys, air pressure means the pressure of all the gases in the air together. And guys, do the units of pressure matter? Would I get a different answer if this had been atmospheres and atmospheres? No. Oh, I misspelled torr. Okay. As long as your units of pressure are the same, doesn't matter what the units are. Remember that number 2 is connected to number 1. You may need a piece of information from number 1 in order to do number 2. Can you guys tell me what piece of information from number 1 will remain the same in number 2? Yeah, the mole fraction. Just because you change the pressure of the container, in this case we're compressing it, your mole fraction is still the same. That's not affected. Okay, so guys, those were relatively simple partial pressure questions. Let's look at one that is more AP level. Okay. Okay. So let me first help you understand what this picture even represents at all. Okay. What we have is a completely closed container. These X's represent valves, and right now those valves are closed. And what I have in this part of the container is I have an amount of methane gas, nitrogen gas in this part of it, oxygen gas in that part of it. Okay? And right now they are completely separated from each other. I give you the volume of each gas. It says when these valves are opened. Now, first tell me just conceptually, what's going to happen when you open those valves? Yeah, they're all going to mix together. Okay? Is the total volume of the container going to change? No. Okay, let's say this container is made out of glass. Okay? So the volume, when you open the valves, that's not going to change. When these valves are opened, what is each partial pressure? Okay, and you might be thinking, well, you know, isn't the partial pressure just going to stay the same? Well, no, it's not. Remember what I said. The way to visualize pressure. Imagine how many hits on the side of the container. Okay? The more hits there are, the greater the pressure. Well, guys, think about it. Just focus on one of the gases. If this gas is allowed to spread out in this much bigger volume, what do you think is going to happen to the number of hits on the side of the container? Are they going to go up or down? Down. There's much more room to move around in. These methane molecules are not going to strike the side of the container as often. So the new partial pressure of methane should be less than 2.7. Now, I don't tell you what it is. You've got to figure that out. Okay? They also want the total pressure, but focus here first. Okay? This is a tricky problem. I will give you one hint. Boyle's law is involved. Do good science. All right, check your answers. You had to deal with each gas individually. And I thought of one side of Boyle's law as the before the valves were opened, and the other side is after. How do you get the total at the end here? Yeah, add them up.